Your presenter today is Richard Penn. He's the Senior Product Manager in Valmet's North American Fiber Technology Unit. After getting his BS in chemical engineering, Richard worked at Domtar, starting as a process engineer and progressing through several positions, including pulp technical assistant, woodyard superintendent, and pulp mill maintenance superintendent. In 2014, he joined Valmet and is currently handling digester aftermarket products and services. Richard will start off with an introduction and brief history of digesters. He'll then continue by looking at common issues with overloaded digester systems and possible solutions, how a continuous digester audit works with respect to chip flow, sizing, specific load, retention time, screen loading, and Valmet digester simulation. Next, he'll cover the benefits of the Valmet feeder adjustment kit and CL1000 chip level sensors. Finally, we'll allow 10 to 15 minutes of time at the end for questions and answers. Over to you, Richard.
Thank you, Ward. Good morning and good afternoon to everyone on the call. Let's begin with a brief introduction of the history of Valmet and the continuous digester. So Valmet can trace its roots back to the original Kemir organization that was headquartered in Karlstad, Sweden. That was a joint venture among three groups from Sweden, Norway, and Finland. And in the late 1940s, they developed the continuous digester, which became very successful around the world. And as time moved on, they continued to sell more and more digesters, starting them up. And then in the late 80s, the KMW group out of Sweden exited the joint venture. And then soon after that, in 1994, the Kemir organization split up. So for us in North America, the Kemir Inc. group that most of us are familiar with became Alstrom, ultimately become the Andritz that we know today. And Kemir AB, that was from the Karlstad, Sweden office, became Kverner Pulping, which later became Metso, ultimately became the Valmet that we know today. So Valmet has been present in the continuous digester technology since the beginning, with many startups around the world. The development continues today through the Valmet continuous cooking technologies that we offer with the new digester systems. And over the years, Valmet has worked to apply these newer technologies that are offered with the new systems back to the older conventional systems that most of us here in North America are familiar with. You know, North America has the largest installed base of continuous digesters in the world. And many of these, are older systems that have been running for many years, that are operating well over the design rates. And as a result, they're more sensitive to disturbances in the process. And so for those that have worked with a continuous digester system, we all know that there are many common issues that are found with overloaded systems. And what you see on the screen here are just a few. We see issues from the chip bin through the feed system, the digester vessel, flash system, basically across the entire digester system. And since each system is different, they have many unique issues that require a thorough investigation. So from these common issues, we also get common questions from our customers. The first being, we have a problem with blank. What does Valmet have to help with that issue? And also, the customers want to run more production. What is the maximum production that we can achieve from the digester, and what is needed to get there? So when you look at what Valmet can offer, we have solutions across the entire continuous digester line, from the chip bin all the way through the vessel to the blow line. So these upgrades can improve reliability, runnability, and several are shown here on the screen. So with years of experience in the continuous digester, Valmet can offer that OEM product knowledge along with new technologies for the system. And today, we're going to be reviewing the Valmet continuous digester audit. That's the approach that Valmet likes to take in reviewing an overloaded digester system. So the Valmet Continuous Digester Audit is a process audit that's tailored to meet the needs of the mill. So we focus on whatever that specific need is, whether it's a production increase that's planned, quality improvements, or just the overall reliability, availability, improvement of the system. And the intent of the audit is to address the system issues, not just the individual components and the issues of those, but really, since all of those issues are often interrelated, it's a holistic approach to evaluate the entire system. We began by looking at the existing equipment, at the current conditions, and really look and see how those compare to design. This allows us to identify causes of the system disturbances or bottlenecks in the process. And on the next few slides, I'll show examples of some key design calculations and evaluations that we use, as well as some considerations around the digester vessel design. Following that evaluation, we're able to provide recommendations to improve the current conditions and system performance, as well as any considerations for future operation with increased production or things like that. As part of the digester audit, in addition to the equipment evaluation, we utilize some proprietary simulators to model the digester system. This helps us identify more of the root cause as well as the optimization opportunities for the digester itself. And this portion of the audit is very helpful when considering changes to the digester system for future production, as well as when there are multiple changes that happen. We can use those simulators to review all of those at one time. And I'll show some examples from the simulators later in this presentation. One of the first things that we look at when it comes to digester design, one of the fundamentals, is the chip flow. Chip flow is calculated based on the target production, the chip bulk density, and the overall digester yield. The chip bulk density and the yield are often the more difficult parameters to understand, but they are definitely key pieces of information in order to arrive at the correct chip flow. And these are typically established from laboratory tests or cooking trials in the case of a new digester system, or often the mill have performed those tests on their own, and so they have that data. Chip flow itself is really the single most important parameter when we evaluate the digester system. We use it to evaluate the sizing of the feed system equipment. An example would be for a low pressure feeder for a given chip flow and a given size of feeder. Does it have the proper capacity? Is it operating at the correct filling degree? If not, can the speed be increased to get to the appropriate filling degree, or do we need to get a larger size feeder? That's the type of evaluation that we do for all of the digester equipment from the feed line through the digester. And then also we use that chip flow to evaluate the loading of the digester vessel and the retention times, and we'll get more into that in the next few slides. When we look at the maximum production from the digester, we often discuss the digester specific load, or the chip load from the digester. And what chip flow is by definition is basically, what specific load is by definition is the chip flow divided by the cross-sectional area of the digester vessel taken at the extraction screens. Through experience over time, we've seen that digester operations can be compromised whenever that chip load is well above design. So most digesters were built for around 15 cubic meters per square meter hour of chip load. I know that's a strange unit, but basically it derives at a velocity of the chip columns through the vessel. And what we've seen through experience and is illustrated in the graph to the right is that as that loading approaches the mid-20s, that's when chip column movement issues can be seen. And what we've seen through audits and evaluations of digesters around the world there are very few digesters that can really achieve anything greater than a 30 chip load. And even at that point, anything in the mid-20s, it's critical to have good chip quality to ensure good runnability. So in the graph, you can see typically at design, the digesters were at the 15 specific load, and they operated with a countercurrent upflow in the digester. But as that loading increases, what the operators are forced to do, the mills are forced to do, is transition to a concurrent type cooking process or a downflow cooking process because of the excessive loading in the vessel. It's also important to know that this is one of the most difficult ones to overcome for folks that are looking to increase production. When the chip load is high, there aren't really any avenues to address the high chip load because there is simply a constraint of the overall digester vessel size. Next, we'll talk about retention time. That's another key design consideration for the digester vessel. You can see the calculation there using the volume of the zone in the digester times a packing degree. And again, we see the chip flow, that very important parameter that's used throughout the design. To explain packing degree a little bit more, we get the packing degree from the Valmet simulators, and the illustration to the left is showing you what packing degree really is. So by definition, a packing degree of 1, you can fit 1 cubic meter or 1 cubic foot of loose chips, 1 cubic meter or 1 cubic foot of volume. That's typically the packing degree that you'll see at the top of the digester. And as the chip column is formed, as the cooking is happening through the digester vessel, that packing degree will increase as the chip moves through the digester. So at the bottom of the digester, a typical packing degree will be in the 1.8, 1.7 to 1.9 range. And again, what that's telling you is you're able to increase the amount of chips in a given volume. So there's less void space around the chips in the bottom of the digester. The overloaded systems that we see are often far from the design conditions for retention time. The illustration on the right shows you some typical design retention times for a single vessel hydraulic digester. Other digester types have similar times, but are a little bit different depending on the vessel design. And when you depart from those retention times, it can have impacts on the digester performance. And what we do through the audit is really look at what those retention times are and provide some recommendations of what can be done, whether it be modifications to the digester vessel to change the process zones, extending the impregnation zone, cooking zone. Those are typical retrofits that can be done for the digester. So a good understanding of what the retention time is key to that evaluation. The third thing that we look at when it comes to the digester vessel and capacity involves the loading of the screens in the digester. In almost all cases, the flow resistance is in the chip column itself and not in the screen. So for a hydraulic digester that has cooking circulations or for an extraction zone in the digester, you're trying to pull the liquor through the chip column and through the screens to exit from the vessel. So in nearly any case, that resistance is in the chip column. And so what that means is that you need adequate time for the liquor to pass from the center of the chip column through the chip bed to the digester wall. And that time really equates to overall screen zone height. A typical design based on, again, many years of experience with continuous digesters is around 15 air-dried metric ton a day per square meter of screen area. And what we see is that as that loading increases in the 17 to 19 or even in the low 20 range, that's where folks start seeing issues with limited extraction, plug screens, and circulation issues. So the answer to reducing the screen loading is something that can often be done with additional screen height. And that's something that we review in the audit to see what the best approach is in order to achieve a reduced loading. The next thing that we look at in the audit, we use the Valmet simulators to really review the digester operation itself. So we have two simulators to do this, and one is Valmet PackSim, and that's used to evaluate the chip column compaction and the overall driving force, the forces that are moving the chip column through the digester. And what PACSIM does is it's a model that divides the digester from top to bottom in several cross-sectional segments. And so a balance is done across those segments in order to develop that evaluation, the total picture of the digester. So we simulate the runnability of the digester by modeling that interaction with the liquor flows, temperature, chemical concentrations, and kappa. CrossSim is the second simulator that we use, and it's a little bit different. So here we're looking at the process conditions, but in this case, not only are we looking at it from top to bottom, but we're looking at it radially across the digester, from the center to the digester wall. So here we use CrossSim to help evaluate the homogeneity of the cook. So we divide the cross section, we divide the digester again from top to bottom into several segments, and then each of those segments is divided into 10 concentric rings, and a balance is done between the rings and between the segments. So we're trying to evaluate the similar parameters here, but again, not only in the vertical direction between the segments, but also across the chip column itself for each of those rings. So we use those simulators to really get a better understanding of how the digester is performing. And then also, once we match the simulator with the current operation, we then know that we have a good model that we can illustrate different operating scenarios and what the impacts are. So whether it be increase in extraction, increase in the production rate, change in kappa targets, so on and so forth, there are many different parameters that we can model and better understand what the impacts are. So here's an example from PACSIM, and the results from the simulators are presented in graphic form. So what we see here is a digester that's laid on its side. So on the x-axis, that's the height of the digester, 0 on the left-hand side at the bottom of the digester, and the top of the digester being on the right-hand side. The parameter that we're modeling is the y-axis. The colored bands on the graph are the locations of the screens in the digester. So this is an illustration of a single vessel hydraulic digester. And what we're modeling here is the chip compaction, or the packing degree through the digester itself. And we're showing 3 different chip bulk densities. And what we're trying to illustrate is really, the impact of bulk density on the overall chip compaction. And you can see, like I mentioned earlier, we want to see a well-running digester will have a final packing degree of approximately 1.8. So if you're above that or below that, that can really impact the runnability of the digester, whether it be too high of compaction prevents liquor from penetrating the chip column, so you end up with runnability issues of not being able to move the column. That's why often the dilution factor is reduced at the higher production rates. And then too low of a packing degree can have its impacts throughout the digester on screen pluggage and circulation issues. So this is a pretty simple example of really illustrating what the changes are with a change in bulk density. So for CrossSim, here's another example, and you can see the graphical results are very similar, but you see multiple lines in this case, and that's what we should see are 2 different examples here. The blue lines being a high specific circulation in the cook zone, and then the red being a lower specific circulation in that same cooking zone. And you'll see that there are 10 lines for each of those, 10 red lines, 10 blue lines, and those are those 10 concentric rings that we're talking about for each segment. So you can see from the upper circulation on, you can see the gradient start to form across the chip column in both of these scenarios. But what I really want to highlight is the impact on the final kappa at the end of the digester. And what you can see, the red lines at a lower circulation has a significant kappa gradient across the digester. The higher circulation has a considerably smaller gradient across the digester. This shouldn't be surprising. I think we all understand the impact of having an adequate circulation flow in the cooking zones to help maintain a good even temperature across the chip column so that you get good even cooking and an even capping coming out of the digester. So this is really a simple example, but where this gets more interesting and more powerful to the user is when multiple changes are made at the same time and really trying to understand and quantify what the change will actually be. That's where the simulator really shines, is being able to perform this type of evaluation, as well as the other evaluations on the alkali profile and temperature profile in the digester. And you can do all those simultaneously. And to the average person, it can be very difficult to understand what the true result will be, but it's easy for the simulator. What I just reviewed is really some key items to evaluate the digester system. In the audit, we review what we discussed today along with many others in order to really get a full picture of the overall system performance and identify the root causes of what the limitations are in the system. Another benefit of the digester audit is it provides that plan, basically the roadmap of short-term and the longer-term process improvements. In many cases, the alternatives for these improvements are suggested in the report, and those help with the investment decisions and the justification for those capital expenditures. We provide a written report that's very detailed and written very objectively. It doesn't contain sales arguments, and the reason for that is so the mill can take that report and present it internally to be used to present the case for why the issues are happening and what some recommended solutions are. And those solutions are coming from Valmet, a group that's been involved in continuous digesters from the beginning, with many years of experience on digesters from around the world. In these digester audits, there are a few common themes that come, and one that we see is that many mills have trouble with the high and low pressure feeder adjustment. Inherent to the feeder design is that both of these have a tapered rotor and a tapered housing that allows the rotor to be adjusted to maintain the clearance between the rotor and the housing. Valmet recommends that we do that adjustment twice a week, somewhere between an eighth to a quarter turn of the hand wheel, and make that adjustment so you're maintaining a good constant motor load on the feeder. But what we see is that many mills have trouble with this, or they don't adjust it, particularly in the low pressure feeder case. And there are many issues that result from that. Irregular stops, trips, things like that from the feeder. Excessive wear by improper adjustment. If you're not making routine adjustment, then you do a significant amount at one time, that can cause you operational issues. Additionally, the lack of adjustment can lead to those issues as well. So lack of routine adjustment, that feeder is going to wear in a certain spot and then make it difficult to move the rotor in past that sweet spot, if you will, from where it likes to run. And then ultimately, for a high pressure feeder, you're adjusting that feeder to control the leakage. And then similarly, for a low pressure feeder, controlling that leakage of steam through the low pressure feeder can make a big impact in filling of the tip meter itself. So to help with the adjustment issues, Valmet developed the feeder adjustment kit. This is an easy way, a safe way to adjust a low pressure or a high pressure feeder. So what we're doing is we're replacing the hand wheel with an electric gear motor that's mounted to the feeder so that you can adjust the rotor position with the touch of a button. We have the feeder adjustment kit that's available for any model of feeder, whether it's a high or a low, and it really makes a difference on the overall ease of operation for the feeder. So a few of the benefits here I'll go through. Number one, it's very easy to install. We have kits that are available for any feeder size. In most cases of a high pressure feeder, at least, all the parts are reused except the hand wheel. The locking pin goes away. This kit can be installed on site if the mill chooses, as long as the pre-work is finished ahead of time. That's the electrical portion of the project. The mechanical portion, actually installing the kit on the feeder, can be done in a routine one-day outage. Or if the mill prefers, we can do the installation back at one of our service centers. So as part of the feeder rebuild, we can offer this kit as a bundle and allow for some savings for installing that feeder adjustment kit on the feeder while at the workshop. The main reason of having a feeder adjustment kit is really to help the operators, to make it easy to adjust and make it an accurate process to adjust. Mounted near the feeder is a electrical enclosure. That enclosure will have the PLC electrical contactors and also this HMI touchscreen display. And so that allows you to control that rotor position with the touch of a button. Also mounted on the gear motor is an encoder, so that tracks the rotor position. That can be fed back to the DCS, to the data historian, so that you can keep track of the rotor position over time, and that can help keep it on top of the operation as well as planning for the next change of the feeder. Another benefit around the feeder adjustment kit is the reduced risk for injury. Because we're pushing a button and letting the gear motor do all the work, moving the feeder in and out, that eliminates the hand wheel. It eliminates the valve wrench or the cheater pipe or the chain hoist that we've seen used to move the feeder rotor in and out. And so if we can eliminate those safety issues, potential back strains, replace that with a push of a button, it makes life easier for the operators at the mill. Additionally, the way the kit is set up, it has a finer resolution than the existing locking pin arrangement on a high pressure feeder. So currently, in order to get the pin locked on a high pressure feeder, you're moving that rotor 0.2 millimeters. The feeder adjustment kit has a finer resolution of 0.1 millimeter that allows for an easier adjustment. And ultimately, if you're making smaller adjustments to the feeder, it can lead to longer service life between rebuilds for the feeder because you're less likely to have any materials that build up between the rotor and the housing or jams, rotor wears, things like that. Another item that we often see through the digester audit is that mills have erratic and unreliable chip level indication. I think most of us understand what chip level indicators are. We're trying to measure the overall chip level in the vessel, whether it be the impregnation vessel or the digester. And chip level is important that we understand what the chip level is so that we can control it. We need to control the chip level so that we have good retention time and good uniform conditions throughout the cooking process. So like we mentioned earlier, there are only so many minutes in the vessel for retention time, and if your chip level is varying, obviously that affects that and introduces variation into the process. Most of the systems out there, whether it be a Valmet system or a competitor system, is using a similar concept in that there's the mechanical sensor that's mounted on the vessel. There are electronics that measure the signals from the sensor, and then a level is calculated from that. Most often we hear people refer to these as strain gauges, and that's what many of these systems are strain gauges. But a Valmet CL1000 is not a strain gauge, and I'm going to explain a little bit more about what that is in the next couple slides here. But first, let's talk about chip level. When I mentioned that we see mills with erratic, unreliable chip level, here's a good example. So here was a 3-sensor system in a hydraulic digester. And you can see that the upper and middle sensors really have no correlation, don't seem to be measuring correctly at all with the overall combined level. The lower sensor has activity, but it's really difficult to correlate that lower sensor activity with the overall level in the digester. And this was an old system with strain gauges. We replaced that system with a CL1000 system, and here you can see a much better response in correlation with the combined level. The lower sensor you can see has good activity, the middle sensor as well, and both of those are correlating well with the overall combined level. The upper sensor you can see it's got very little activity, and that comes down to how they're operating their digester and really trying to maintain the level a little below the upper sensor so they can have a little time to respond if they run into upset conditions. But overall, you can see a much better indication from the digester chip level indicators. And the result from that is that allows for the better control of the digester chip level. And so how a CL1000 system works, typically you're going to have 3 to 5 sensors on the vessel with a single vessel hydraulic or steam liquor phase digester. It'll be a 3-sensor system. A 5-sensor system is pretty common for a 2-vessel hydraulic digester. So those sensors are mounted on the digester. There's a electronics cabinet that's mounted either in the field or in the MCC in an enclosure. And the principle is similar to the strain gauges in the fact that we're trying to measure the chip level by the weight of the chips above the paddle. So the chip column above the paddle is going to exert a force on the paddle. The paddle is going to move and the tube that it's attached to will twist. And here's where the difference comes in between the CL1000s and the strain gauges. The reason strain gauges are called strain gauges is that they have a strain gauge mounted to the tube so that they're using a resistive type measurement to measure the strain on the tube as it twists. For a CL1000, we use a differential transformer. So we're measuring the twist of the tube, but it's indirectly. So we measure it indirectly by these differential transformers, and what those are is a set of coils with an air gap between them. As that air gap changes, it changes the voltage. That voltage is converted to a 4 to 20 amp signal, and then those signals are used in the overall chip level calculation. So the CL1000 system, there are 2 different systems depending on the application, whether it's a steam liquor phase or vapor phase digester or a hydraulic or impregnation vessel, I'm sorry. And it's also key that the sensors are installed in a good location on the vessel. The location of the nozzles and the sensors plays a big role in the performance of the overall indication. And that's something that we review on every project to look and see that the vertical and horizontal distance between the sensors is acceptable. In most cases, we can reuse the existing nozzles in their existing locations. The CL1000 use a 10-inch mounting flange, which is very typical of even the older strain gauges that are out there. So it makes it a pretty simple installation to upgrade to. Some of the benefits around the CL1000 is that we are measuring the chip level by mechanical forces, so we don't have to worry about foam or liquor impacting the level. These are completely seal welded. This is a big difference from the other sensors that are out there. Because they're completely seal welded, that means you don't have to grease the sensor, put the grease in there to act as that sealant between the liquor and outside. So that makes it a very maintenance-friendly sensor. There's very little to do on an annual basis. Strong design, there are no shear pins. It's built to withstand the weight of the chip column. No concerns there with needing shear pins in the sensor. No seal water. Again, they're seal welded. Most of the older systems are now using grease instead of seal water anyway. But really the biggest benefit around the CL1000 sensors really comes from the easy maintenance and calibration. All of the electronics, all of the components that can have issues are mounted externally. So that allows for any type of repair or calibration to be done on the run. So this means if you want to do a calibration on a sensor, you can do it on the run. You don't have to wait till a shutdown. You don't have to take the sensor offline until you have the opportunity to work on it or pull the sensor from the vessel. It's very easy, user-friendly process, a quick process to do that calibration, and typically that's done on an annual basis. So the routine maintenance associated with the CL1000 system is very user-friendly. To summarize, digesters in North America are often overloaded, often grossly overloaded, And as a result, they're very sensitive to disturbances in the process. And many of the systems out there have these issues that y'all deal with on a regular basis. An audit that we do on the continuous digester is the Valmet preferred approach to evaluate the system. And again, the real reason for that is so that we can evaluate the system as a whole and understand what the issues are instead of just the individual components. So we get a good understanding of how each part, each little issue that comes up, how that influences the overall performance of the system. Good chip level measurement is needed for proper control of the digester level. That's where CL1000s are a great upgrade, a great addition to the digester system, is that they are a very good sensor, very robust sensor that provides reliable chip level indication. And as a result, you can achieve reliable, good chip level control with this CL1000 system. We talked about the high and the low pressure feeders. This is a common issue. The adjustment of these feeders it's a common issue with many mills in North America. And what Valmet can provide is that adjustment kit to allow a safer, easier way of adjusting the feeder and achieve better results from that equipment. Lastly, I just touched on a few things today, but as you saw at the beginning, Valmet can provide solutions across the entire digester line. And these are meant to make your life easier and improve the operations. And it's something that we would definitely be interested in and welcome any questions that you have around those items.
Thanks for that excellent presentation, Richard. Before we get into the Q&A portion of this webinar, let me say that this presentation is available in PDF form. Simply email Richard at richard.penn@valmet.com and he'll be happy to send you a copy. Now, we've received a fair number of questions already, but you can still submit them during the Q&A period. If Richard cannot answer them today because they need more information or the question deals with confidential matters, he'll be sure to email you a comprehensive answer after the webinar. Richard, take it away for Q&A.
Okay, so a few questions here I'm kind of looking through. One question about the digester audit. Can the digester audit be completed remotely? So the short answer to that is yes. But let me give you a little longer explanation here. So in the past, the digester audits that we've completed have been done on site, and that's typically 2 engineers that are on site for a week, and during that time they're interviewing the mill personnel, talking to the operators, the supervisors, the managers of the fiber line, and making sure that we get a good understanding of the current operation. We're reviewing the system, the equipment, the layout of the digester process and arrangement in the field, and doing all that data collection during that week. Then we go back to the office, and that's where we do the detailed analysis. We review the data that was collected, input information into the simulators and do that review with those and generate the report. That report is sent to the mill. We give you time to review it, and then we come back to the mill to review that report in detail and spend almost the whole day in some cases going through that report, looking through it, answering any questions that you have. So that's the way that we've typically done it. But we all know we're living in an atypical world now. So as a result, Valmet, like other companies, we're looking at how we can service our customers remotely. And so we've developed an audit package that can be done remotely. We do it from our office with the help, of the mill personnel. And then we can also package that with an on-site visit in the future to really complement that remote audit that's done. Now, I will say that when you do an audit remotely, it needs to be well understood that it requires very good communication between the mill and Valmet. So that communication takes time, it takes resources, and the mill has to have resources to dedicate to the audit. And ultimately, that's one thing that can drive that decision whether it's done remotely or whether it's done on site is the amount of resources that the mill has to support it. Because it takes a significant amount of time to gather the information that's needed in order to get a good understanding of the process, in order to get a good evaluation of the process. So those are a few things to consider around a remote audit. There was a question around using an imp bin retrofit to offload an undersized digester or screen upgrades required. So the Valmet imp bin was originally developed as part of our new, or with Kverner as the compact cooking system, now what we call Valmet continuous cooking. And that was an entirely new digester system. But we have the imp bin available as a solution for retrofits of an overloaded system. So an undersized chip bin, an undersized feed system, or even looking at a digester and if the impregnation zone is too short and the cooking zone is too short, can we move that impregnation zone out of the digester into that imp bin, solve those problems? So we do have the imp bin as a solution, and that this is really a good example of how the proper understanding of what the system needs are that we can get from that digester audit. That's what's needed in order to determine what the most appropriate upgrade is for the system. So, it could go either way. Maybe there's a smaller upgrade that you can implement to help with a digester that's overloaded, and an imp bin's not required. Or maybe if you have issues in the chip bin and the feed system and impregnation, the imp bin is the best thing to address that. So it's really a case by case basis, like most of these are. But again, the short answer to the question is yes, we can use that as a solution for an overloaded digester. Another question here: what are the benefits of running a submerged chip column versus a non-submerged chip column? So this would be for a steam liquor or vapor phase digester, and Valmet's opinion on this is that there are really no benefits. We believe that the steam liquor phase digester, it was designed so that there would be a chip level above the liquor level in the digester. So you're controlling both. You're controlling both the chip level and the liquor level in the digester vessel. And that chip level above the liquor is there to provide, really several tons of force on the chip column so that we can help move the chip column through the digester. So if you submerge those chips, if you're running liquor level above the chip level, it negates that control knob that you have, if you will, to help control that force of the chip column. So, from Valmet's perspective, we supply steam liquor phase digesters today with our new cooking systems, and they run with a typical steam liquor phase top that has a controlling the chip level above the liquor level in the digester. Another question here how do you adjust the feeder on a power failure if there's a feeder adjustment kit? So if there is a power failure, obviously the electric gear motor will not operate on the feeder, and in most cases you're going to want to go down there and back the rotor out on the feeder. So I mentioned that the electric gear motor is going to replace the hand wheel and the locking pin. What I didn't mention is that that gear motor, we're able to remove that locking pin on the feeder because the gear motor has a brake. That prevents the motor from turning, prevents the gear box from turning, which will prevent the rotor from moving in or out on the feeder. So in the event of a power failure, what you do is you go down, you can release the brake on the gear motor, and the motor itself has an extended shaft on the fan end of the motor. So once you release the brake, you can take a wrench or a power drill with the right bit and power the the gear box through the motor with that drill. So you're able to move the feeder out manually without having electricity. And then once power is restored, there's a process there to get the feeder back in the appropriate position, make sure that the PLC knows that position. Remember, there's that encoder, so we're tracking the position. We need to get that reset, and then it's back to normal operation once the power's on. One more question here. What have you found to be the optimum way to control chip level in a single and dual vessel hydraulic digesters? So, what we do typically, you're controlling digester chip level with by control of the blow flow in the digester, and here it goes back to, in order to have good control, you have to have good measurements. You can't control what you can't measure, and that's where the CL1000s really come into play, is that you have that reliable measurement. So whether it be a hydraulic digester or a steam liquor phase digester, single vessel or two vessel, you've got the good indication there to help with overall control. And like I mentioned before, in the case of a steam liquor phase digester, being able to have good control of that chip level above the liquor level is key, so that we're controlling the overall driving force and packing degree in the digester. We want that to be consistent. And then, for a two vessel hydraulic digester, the two vessel hydraulic digester is not well regarded when it comes to overall chip level. The top of the chip column can be quite erratic and non-uniform, and that again, that's where we want to make sure that we have good, reliable indications so that we can control that well. And there are several other questions here that we're not going to have time to answer today, but I will reach out to you all individually and continue the discussion that way. Ward?
I hope we were able to respond to most, if not all, of your questions. I see that there's some more questions about the simulator and providing training and others, cost of replacing strain gauges. We'll get back to the people who asked those questions for sure after the webinar. Richard will follow up via email. We'll also be emailing everybody a link to the recorded webinar as soon as it's available at Valmet's YouTube channel. If you have any further questions, email them to richard.penn@valmet.com or reach out to him at LinkedIn, and he can go more in depth with you about any digester pulping needs you may have. We hope you've gained some valuable knowledge about optimizing your continuous digester operations today that can help you in moving your mill forward. Thank you all for giving us your time today, and we hope you'll join us at future Valmet webinars. Bye-bye.